Good. So thanks everybody for joining us for this first Heidelberg Joint Astronomical Colloquium of the semester. I have here an attendance sheet. This is so I get reimbursed for the snacks. So just put your name down. We're not really paying attention to this list except for that. And with that, I'll let Mike introduce our speaker for today.
By the way, shortly before I introduce Daniel, we have drinks with PhD students and postdocs with Daniel right after. And so just let me know if you'd like to join or just follow me after the colloquium. And we also have dinner at Dorfschenker at 7 p.m. It should be not a problem to add a few seats onto the table if you haven't told me that you'd be joining before. Okay, and it's an honor to introduce Professor Daniel Price from Monash University. Daniel is usually from in the very faraway city of Melbourne, Australia, but we're very lucky to be able to borrow him here while he's on a sabbatical at IPAG in Grenoble. So Daniel's academic career also started at Monash University, where he completed an honors year working with Joe Monahan, one of the founders of the smooth particle hydrodynamics, or SPH method. Daniel then completed his PhD at Cambridge under the supervision of Jim Pringle in 2004. He then spent time at the University of Exeter as a Royal Society University Research Fellow and a PPARC postdoctoral fellow. In 2008, Daniel returned to Monash as a lecturer and was later appointed a professor. So Daniel has made many important contributions to computational astrophysics, especially in SPH. He's the developer of the Phantom Code, which I'm sure he would talk about, which is used by many different communities. And his application of SPH are very broad, ranging from star and planet formation, accretion disks, tidal disruption events, and more. So let us welcome Daniel and hear from him now.
Well, first of all, just thanks to Mike and Catherine and Ian and Miriam and everyone else who's been able to organize my visit to Heidelberg. I feel very welcome and very honored. So thanks for having me, especially all for turning up in the rain, coming down from your various institutes. So I really appreciate you being here. Perhaps it's because I've spent too much time sitting in French coffee shops, staring at nice squares and thinking about life. But I'm also starting to get old, so you start to reminisce about how it all fits together in the bigger picture. So I'm going to try and do that today, which is cover what I think is an arc of a story, which I hope at the end you just go, well, that's obvious. But it's something that maybe is dawned on me slowly. Maybe that's just because I'm a little bit slow. But it's just that how accretion works in the universe. And so this is something we've learned a lot from in the area of protostellar disks, because as you'll see in a minute, that's where we've been doing the most observations recently. And you learn much more from looking at things than you do from calculating things. But then I'm going to try and relate that to the sort of process more generally about how you accrete things onto any object. So I hope you take away something general, even though I'm going to talk about some things which are specific. All right, so what is the problem of accretion? The problem with my mouse is that it's not on. Okay, but the problem with accretion is something like this, is if you want to accrete material onto the sun. So for example, we have a nuclear waste problem. We would like to send our nuclear waste to the sun. What's the problem? Well, so lifting it off the Earth, that's step one. So say we lift it off the Earth, we send it in the direction of the sun. All right, so our next problem is angular momentum. So angular momentum in the universe is a conserved quantity. And conserved means you cannot dissipate it, you cannot lose it, you must give it to something else. So you send your nuclear waste, the problem is that's not what happens, that's what you'd like to happen. But of course the Earth is orbiting the sun, and so if you send a little bit of nuclear waste radially towards the sun, it's just going to go straight back out. It has exactly the same amount of angular momentum, and you'll just meet your nuclear waste later on, and it won't be good for the planet. All right, so the problem of accretion is how to land things which are far away onto small objects. That's the basic process. And if you were like me, well, I was brought up in a school of accretion disks. This is how we thought about how accretion works. So this is the kind of standard picture where you write down a viscous accretion disk. And basically this is what we think of as the ring spreading kind of model, where material will land in orbit. So this is radius from your central object, and this is sort of surface density of material. And if your material is in the form of a gas, you're going to have some sort of dissipation. You're going to give a viscosity where rings will interact in your disk, and material will spread out. And this is the sort of standard way we think of that nature solves the angular momentum problem. Okay, so why does this solve the angular momentum problems? Well, first of all, you can see that material is accreting onto the central object. That's what we're trying to achieve. But the other thing in this diffusion process is that you get a small tail of material carried a very large radius, which is then carrying all the angular momentum. So as we say, there's no material goes to infinity with all of the angular momentum. All right, so this is our sort of standard picture, is that to do angular momentum transport, you have to form a disk. And then the discussion goes, well, what is the thing that's causing the rings of material in a disk to interact? It's presumably some kind of turbulence, and therefore, what kind of turbulence do we need? All right, so many lives have been spent over the years in investigating ways of transporting angular momentum in disks and making turbulence. All right, so one of the most obvious, of course, is simply gravitational instability. So if a disk is unstable to its own gravity, the disk will want to collapse, but you will make spiral arms. These spiral arms can heat the disk, and it can sort of self-regulate into this gravi-turbulent state, which is a kind of large-scale turbulence in your disk, which is therefore doing the job of mixing material between rings and transporting angular momentum. Okay, what's wrong with the gravitational instability? Well, you need a disk which is heavy enough to start to collapse under its own gravity. All right, the next most obvious mechanism. Well, not obvious, actually. It was not obvious at all. It was a big discovery in science. Well, the question you should ask at the end of every talk, which is what about magnetic fields? So Balbus and Hawley, of course, famously discovered, so there was an old problem about trying to see if disks were unstable to some kind of instability. So you're seeing gravitational instability, but it requires special conditions. So the MRI was the obvious one, which solved a lot of problems for people theoretically, because instead of needing, well, so hydrodynamic disks, people looked for all kinds of nonlinear instabilities. They don't seem to exist. But the MRI, you are linearly unstable. As soon as you put in a weak magnetic field, you generate a kind of sustained turbulence, and everything works. Accretion disks do their thing. There's a little problem, which is that you need things to be ionized. And unfortunately, in the one class of disks that we can observe, nothing is ionized. And the MRI just doesn't seem to be operating in the regions that we can observe. Doesn't mean it's not there at all. Okay, so jets and winds and outflows. So this is just an example I had lying around, but plenty of other people have worked on making outflows via disk winds or jets. So this is not a kind of form of turbulence at all, but you can just lift the angular momentum up instead of trying to make this kind of turbulent ring interaction pattern. And so some of the discussion that's going on in protostellar disks at the moment is whether we're kind of doing a sort of more viscous-like evolution disks or some sort of wind outflow-driven accretion. And this is an interesting discussion. Okay, there's even some suggestions in the literature that maybe even planets can be the source of viscosity in disks. So this is like Goodman-Rafikov, for example, were proposing this. But why is a planet a source of viscosity? It's simply because you derive spiral arms in the disk, and this is what induces then mixing between rings, gives you angular momentum transport. All right? Sounds too easy. Okay, so how can we observe accretion disks? This is all theoretical. How can we observe accretion disks? Right, so let's start by discussing accretion disks you can visit. Okay, so actually I forgot to quote the quote. So if you quote the accretion disk review from Jim Pringle, 1981, he said basically, actually I like this, if you want to write lots of papers, you can think about sources of viscosity in disks. But we're more likely to learn by actually observing them than just by sitting around thinking about theory. All right, so let's talk about accretion disks you can visit. The solar system, of course. So the most obvious way we think about planet formation is that planets orbit more or less in a plane, and therefore we assume that they formed in a disk. Right? So some kind of disk had to exist in order to make the solar system. What else is an accretion disk we can visit? Exactly. And so Saturn's rings is actually a fascinating set of objects, or millions of objects, in fact. But it also tells us that things are a little more complicated. And actually, there's some good analogies here for what's going on in protostellar disks. So for example, Saturn's rings, the Cassini discovery is that if you fly through the ring plane, measure the mass, then the fact that the rings are not dark yet requires you them to be fresh. So Saturn's rings are not some leftover from formation. They're probably some recent tidal disruption of an icy moon. So they're actually freshly created and probably actively forming moons. Well, in fact, the only reason they don't form moons is because that's inside the rush lobe. But as soon as you get out the rush limit, as soon as you get outside the rush limit, you see moons. In fact, you see moons feeding rings. So the fact that that's fresh is interesting. You also see some of the processes we're going to talk about, which is, you see waves excited at Lindblad resonances by embedded bodies. And you see very directly gaps carved by moons or resonances with moons. And that's, again, a lot of what we think is going on in protostellar disks. All right, what about the solar system? Is it all neat and sorted out? Do you think it all formed in a nice, neat disk? Conserving angular momentum, everything's happy? Yeah, so if you look a little deeper, scratch a little beneath the surface, what doesn't quite hold up in the solar system? Just some small things. Remember angular momentum, everything should be going in the same direction. Is it? Not quite. So the sun is off by 7 degrees, and off is a lot in angular momentum terms. It means it doesn't rotate in the same, doesn't spin in the same plane as the plane in which the planets orbit. Okay, awkward. Anything else? Well, okay, so there's lots of hints in the solar system that things were a little more violent. So for example, you have radioactive elements which are short-lived, which presumably were spewed into the interstellar medium by nearby massive stars. You've got some really weird phenomena, like the fact that all the dust you find in meteorites has been meteorites are defined as being chondrites half the time. And the ones that aren't chondrites are just because they've been melted inside asteroids. But the fact that dust is melted is actually quite hard to do. If you ever look at a protostellar disk and ask someone, what's the temperature of a protostellar disk? Miriam? Give me your average disk temperature. 50K, yeah, but you'd never say 1,000 Kelvin, right? So to get this kind of stuff, sorry to put you on the spot there, but this kind of stuff needs processing at very high temperatures. So, beyond 1,500 Kelvin, you need to be able to melt stuff. How does that have anything to do with formation in a cold protostellar disk? All right, you have also some hints just from pure rocks that things were a little more messy in the beginning of the solar system. So we have these two families of chondrules, so the non-carbonaceous, carbonaceous, that independently have been thought about this story that there's some fresh infall of material that happens like later on in the disk formation process. Okay, so they're all just clues, and really they're kind of hard problems to unravel if you're just looking at the solar system. But they start to make sense if we look at the way that planets form elsewhere. Another weird thing I'm going to come to is the solar system really just ends at 47 AU in the terms of the material in the plane is very sharply cut off. I'm going to come back to this a little later on about why that might be. And what's after 47 AU is spewed on these eccentric and inclined orbits. And it's not obvious why that should be, but I'm going to give you a good reason why that might be. All right, so what's new, and I would never dream that we'd see things like this, is we can now just take pictures of disks around other stars. So we don't have to guess about the kind of disks that the solar system formed in, we can just take pictures. And just take pictures is a very big generalization, I know, for what's a complicated process of subtracting starlight. But this one's pretty basic. This is really polarized differential imaging. So if you look at light off a table, it's polarized because it's reflected to you, whereas light coming straight from the source is unpolarized. And so, for example, when polarized differential imaging, you just see the light reflected off the disk, and you only plot the polarized component, you see a picture of the disk instead of a star. Yep, so it's pretty simple. Yeah, but of course, this is with the sphere instrument on the Very Large Telescope. But you also get a very complementary picture at millimeter wavelengths. So ALMA also has the spatial resolution to see inside these disks at the kind of distances of nearby star-forming regions. So you also get simultaneously a picture of what the dust of sort of millimeter emitting sizes, which is sort of 100-ish microns in terms of the grain size, is doing. And that's doing something very different already. So we see that the dust is in a kind of pancake close to the midplane. And we start to learn, well, there's some spiral features and stuff going on that is kind of the theorist's game to then try to unravel. Okay, but there's another tracer of what's going on in disks. And that also comes from the ALMA telescope. Yep, so what can we trace in gas? We can trace molecular line emission. So molecular lines, the most obvious one is carbon monoxide, is the brightest. We can't trace the H2 directly, so most of the disk is molecular hydrogen, but we can't trace it. So instead you get CO emission, and CO emission we can trace in very detailed mapping as a function of frequency. And when you map as a function of frequency, of course, you're probing the Doppler shifted motion of the material. So you can really get a velocity map of what's going on inside as well. All right, so the game observationally is to try to unpack all this to learn what's going on. So this is not a particularly new game. And of course, we now have galleries of these things where we really have, again, the millimeter wavelengths. We see what the dust is doing in the midplane. In the scattered light, we see the light reflected off the bowl at the top of the disk. But you know, the theorist's game is to try to model this stuff and figure out what it's telling us about how these accretion disks are working. Make sense? All right, so already you start to see some odd things. So one of the early results, for example, when people started doing high resolution ALMA images, is that we see these kind of gaps and ring structures kind of commonly. Okay, so if you put a bunch of gaps and rings in front of a good bunch of theorists, what are you going to get? 20 different models for making gaps and rings which weren't thought of beforehand. All right, but we also see things that were not necessarily expected, but we now sort of think are obvious in hindsight, which is there's a lot of hints that things are not neatly aligned. So for example, the shadows cast by misaligned inner disks, the shadows that take up like half the disk sometimes, so things are really quite messy. And we're also going to talk about, you know, some of this stuff, the fact that you see a lot of connection to the environment, so things are not necessarily isolated. All right, so in terms of what all this means, so even if you take the first ALMA observation, which is I'm sure everyone's seen by now, but it's really important to remember the context in which some of these observations take place. So the first ALMA observation at long baselines was HL tau, which is of course now a famous image. But if you just do the fade between the Hubble image of what's going on in HL tau, which is an active young star-forming region, and you fade to the millimeter dust, they're doing very different things. And you can see already this is just a star that's in an active process of formation. And so whatever you propose as the origin of the rings and gaps must be going on in the early phases of star formation. Okay, so when we make modeling, so one of the early puzzles actually, which I'm showing this for sort of nostalgia. It's now, you know, it's 10 years ago, but there's an important point here which remains, which is people were puzzled, and one of the reasons why people went off on models of other things for gaps and rings is that if you think about how planets interact with a disk, you should make spiral wakes. Okay, so why don't we see any spirals in the top image? Big enough? So the key thing is to think about the different wavelengths. So what are we observing? Is it the gas disk? No, so what is it? It's the millimeter emitting dust, which is quite large grains. And those large grains can be quite decoupled from the gas. They don't have to be doing what the gas is doing. And the most basic way they decouple is just to settle. So, and we already see from the ALMA that the dust disk is very well settled at millimeter wavelengths. And so what you're looking at is what the dust is doing in the midplane, which is basically this thin pancake. What reminds you of thin pancakes with gaps in it? Rings. Yeah, what are causing the gaps in Saturn's rings? Moons, resonances with moons, but embedded bodies. Yeah, exactly. Not quite planets, but moons, yeah. Planets around Saturn, I guess. And so the same phenomenon is going on here. So the reason you don't get spirals in the millimeter is just because you're carving gaps in the thin dust disk. And therefore, just like dropping the sound speed so you don't have a big opening angle on your spiral arm. All right, so that's what you really observe. And so, I mean, we started playing this game, so there's lots of other models. But you know, you can really line this sort of thing up, and that's kind of where we started in this game, is trying to line this thing up. And then the implication of this is then what you're trying to learn from theory, what sort of things you need to explain these kind of gaps. And you end up needing, you know, quite fully formed giant planets. And of course, that's not how planet formation is meant to work. It's meant to happen later and take 10 million years. And it's not meant to all be cooked at the 1 million year stage. So it's telling us something about planet formation that we haven't finished unpacking yet. But then there's a lot of argument against. So one of the main arguments against this kind of thing was, well, I can give you 20 other mechanisms for making gaps and rings in disks. Right? What do we do? Just speculate. I like pausing. Everyone thinks a little bit. Well, so what we have is a wealth of observation. So the great thing, actually the terrifying thing in this field is you can make any kind of prediction like this and people go chasing it immediately and tell you you're wrong next week. So how can we observe planet-disk interaction more directly? So just quickly, so you have a star and a planet. So how does a star and a planet, how does a planet interact with a disk of gas? So just like in Saturn's rings, you excite disturbances at Lindblad resonances. So you get basically an inward propagating sound wave, an outward propagating sound wave. But if you think that's a bit complicated, I'm just going to keep it simple. So a planet's just like a duck. And when a duck swims, what is it? It makes waves. Okay, so it makes waves, but this thing is known as the Kelvin wake. So the wake, the kind of V shape made by a duck, is simply the line of constructive interference of all the waves generated by the duck. Comes the duck, here's the duck. Yeah. So planet's just the same. So you have all these waves excited by the Lindblad resonances, and you add them up on the line of constructive interference, and you get this shape of the planet wake. Okay, but what is the difference between a planet and a duck? Right? Trajectory, yes. So when the duck swims, which way does the water go? Goes back. When a planet swims, which way does the water go? Not water, but gas. Inside, so disks are differentially rotating. So the material outside the planet is orbiting slower, so the wake will go backwards. But inside the planet, the material is orbiting faster, so the wake will go forwards. So it's just like a duck, but like that. Yeah? Makes sense? That's your basic explanation of a planet wake, and there's a much more mathematical explanation, but it's the same principle. So the basic shape is just the differential winding of the disk that winds it up into the spiral pattern. Again, this is the line of constructive interference. Okay, but this is important because these wakes turn out to be detectable. So and again, we came back at this the wrong way round. So what we found was a weird thing in a Doppler shift. So this is what you call a channel map, which is just take a slice at a given velocity. And you can see all the material that's moving towards or away from you at that velocity, which takes a weird chunk out of your disk. All right, so if you look at this image, what you see is the CO emits from what's frozen down the midplane. You get a layer of CO emitting from the top layer of your disk, a layer of CO emitting from the back layer. And you can do the sort of butterfly pattern through the disk that I already showed you. But what you see is there's a little weird there's a little weird thing we call a kink, which is where the material is pushed to like a different orbit locally. Okay, so you got something which is very locally disturbing the flow. And basically we didn't really know what we were doing at the time, but now we do, which is what this thing is basically where the wake from a planet or something else causing spiral arms. It doesn't exactly have to be a planet, but I'll show you that this works. When it crosses the channel, you kind of push, you have a velocity perturbation, so you locally push the material into a different emitting channel, and that gives you this kind of ka-chunk in the sort of channel map of the CO emission. All right, if you don't believe me, so that's the sort of the full cube. But here's another example in a different disk. So again, you see this local little kink in the velocity field. And if you look at the opposite channel, so if a disk was just orbiting in a nice axisymmetric way, the opposite channel would just be the symmetric reflection of this thing. But you can see that this little wiggle is definitely not on the other side. And more significantly, the little wiggle is located exactly in the place that would be the middle of the continuum gap. Okay, and some of this might seem like speculation, but it's actually really easy to reproduce in models. So you can make a model of exactly how the channel maps should look from your disk, and you can put a planet in it, and you can reproduce the little ka-chunk at exactly the right location. All right, so what I'm hoping to convince you of is that we don't have to just speculate about whether there's planets in these gaps. We can see very direct evidence of the wake caused by the planet by mapping the wake in the velocity field of the disk. All right, and so in fact, one of the mysteries in the first detection was that what we predicted when we tried to understand this analytically is you should have these other kind of chunks. Basically, every time the wake crosses a channel, you should get a little chunk, but the ones that are closest are the big ones, but you should be able to see some little traces further out. And all we had to do was wait a couple of years and get better data. And once you get better data, you can see this correlated series of perturbations just tracing through the outer disk. So the little kink is basically here, but you can see a bunch of kinks next to it, and you can trace out the pattern of the wake through the outer disk. And that's exactly what you predict from the analytic model of how the wake should interact. All right, so basically from this, you can start to measure a planet mass, which then tells you again fairly directly that there's really a planet that's carving this gap and that's giving you some kind of perturbation in the velocity field. And it's hard to do this with any other model that makes kind of gaps and rings because all those other models tend to be axisymmetric. So it's really a non-axisymmetric perturbation. And of course, this motivated then a large program which Miriam led along with various other people. And so it's been a big program to then try and get good gas kinematics on disks. And so what you saw in the early pictures is this picture of the mid-plane dust. But if you look in the gas and what it's doing, so same scale, I'm just going to show you the CO emission. You can see this booming gas disks. And in nearly every one of them, you see hints of spiral structure. So we haven't completely unpacked all of this yet, and we can't tell you exactly where the planets are. But what we can tell you is there's ubiquitous kind of spiral structure in the gas that indicates some kind of perturbing bodies. All right? So the other way, of course, that we've cemented this picture is just by taking actual pictures. So the reason why this is hard is because most of the time, planets are obscured by disk material. So you need special cases where you can really see in. And things like PDS-70 is the one really good example where you can see in, it's pretty face on. There's a kind of cleared out dust cavity and you can peer in and really get an image. And this one, you have now two directly imaged planets that are, again, by selection effect, multi-Jupiter mass, because that's what we can detect. But the hope is with telescopes coming online, we're going to cement this picture pretty clearly. There's another one by Ian here. Where's Ian? Over there. Yeah, which is, again, you got going back in the archives, you can see there's like a blob which moves on a Keplerian orbit in the gap, which is again face on, you can kind of see down. And there's lots of like maybe candidates here. Direct imaging is really hard. You get kind of blobs everywhere, and you're not quite sure if it's real or not. So there's a lot of arguments about whether things are real or not, and whether things in gaps are real. But some hints also of circumplanetary material around some of these. So we've got multiple lines of evidence for planets carving gaps. And hence, these disks are quite young, and so the implication is that planets must form and grow quite quickly. All right, and we're starting to hint about how they grow as well, but we're not really there with the details yet. But I want to move on to a bigger question that maybe you haven't thought about just yet, which is what's in the middle of all of these disks? Okay, but before I move on to that, there is a clue, which is that, again, these dust disks are thin, so if you want to make planets quickly, it's definitely easier if the dust is settled, and we do observe that the dust is settled. So however you want to do it, streaming instability, gravitational collapse of the dust layer, it's always easier when the dust is settled in a thin disk, and we do observe that the dust is settled in a thin disk. Seems to be some indications that it's taking some time, But if you do some things, for example, you take gravitational instability and you put dust in a disk, you do find under some circumstances that the dust, if it gets into a thin enough disk, it can just collapse. So maybe planet formation is happening in some kind of dynamical way which would fit the observations. All right, but let's talk about the other problem. So the other problem is we've got a star, or stars, and well, we don't have a long time. So these star forming regions are 1 to 2 mega years old. And so just do back of the envelope calculation. Let's not give the answer away. How much do you have to accrete in solar masses per year to make a 1 solar mass star in 1 mega year? Want to feed a star constantly through an accretion disk? 1 over 1 million, yeah, which is 10 to the minus 6 solar masses per year, is the rate at which I would need to feed a star to grow it through a disk. Okay? So let's take observations of all odd T Tauri stars and plot their mass accretion rates. What's the problem here? There is not a single disk observed around a T Tauri star that, well, at least with this in this plot, that is accreting at that kind of rate. So accretion disks that we're observing is not the way that you form stars, and it's not actually the way that you accrete material onto stars either. Why not? Because this is not star growth material. This would take way too long to grow a star. So we do not grow stars by feeding them with disks. Isn't that wrong? Isn't that how we solve the angular momentum problem and get all the material into a star in the first place? Okay, so there's another way of phrasing this. So of course, we don't really measure the mass accretion rate. What we measure is a luminosity from some central region which is thought to be proportional to the mass accretion rate. So this problem is kind of known. So we're basically saying that young stars are too faint. So this is called a protostellar luminosity problem, which is that they're not all accreting at the rate they would need to grow to feed a star in a reasonable time. Yeah, so this is called the protostellar luminosity problem. Basically, they're tiny, alpha's tiny. And there's a well-known solution to the protostellar luminosity problem. Does anyone know what it is? If you take a snapshot picture of a given star forming region, you find that all the young stars are too faint. Why are they all too faint? Why are they not as bright as they should be if they're accreting at 10 to the minus 6? Right? Yes, obscuration, but it's more than just obscuration. Exactly. Yep. So you're 20 years too late, but yes. So the accepted solution is that accretion is not steady, and you don't just accrete at some constant rate for a long time, but you accrete in a bursty way. Okay, so the kind of models that you need to do to, well, what's the bursty mode in stars? So the most outbursty thing we observe is something known as F Uranus type outbursts, which I'm going to discuss in a minute. But basically, if you take a model and you take an accretion rate, and most of the time it's at 10 to the minus 8, so you accrete in this kind of low state, but occasionally you have a burst and you eat a lot of material, and well, whatever you think the duty cycle is, might be like some few big ones or lots of big ones, but the key thing is that most of the time you need to be in this low state, so that at any given moment, if you observe your cloud, you're going to find low luminosity objects. Make sense? Okay, so the question is, what are the protostars doing when they're in this high state? And that's the kind of thing I want to get to. And so one model is that maybe they are violently gravitationally unstable and eating lumps. Okay, but how could we possibly solve this problem about what stars are doing when they're in this high state? We could look with telescopes. Yeah, so we can actually observe some of these things. Okay, but there's also a theoretical reason why you probably don't see a disk observing accreting at above 10 to the minus 6. And that's because the most you can do in a disk is like alpha 1. So if you take alpha 1, then basically, if your disk would be gravitationally unstable, you would be accreting at this rate, which is 3 times the sound speed cubed over g, which is that maximum rate. But of course, if you try to push more material through a disk, all it does is fragment and form planets. So and therefore you don't accrete this material because it's all fragmenting into things which will stay in orbit. So one model is to eat the lumps, and I want to mention that because it is a viable model. But I want to suggest an alternative and think about how this works observationally. Okay, so what we want to look at is the young stars that are in the bursty mode of accretion. All right, so this is a very generous name to call this a class. But there's at least 3 objects that were in the initial class of FU Uranus objects. It's now like maybe 20, but they're all different from each other and they're all special. But the really weird thing, so FU is the classic one. This is 1936. So it was a 16th magnitude star. Basically, in the space of a year, it went from a 16th magnitude star to a 10th magnitude star. And for the last 100 years, so this timeline even continues, this was from 1996, but basically it's just stayed doing that since. It's just stayed in this high state ever since. Okay, and you see similarly fast rises in 1057 sig. So this is a problem, right? So let's think about this a little more carefully. How do you get a disk to like completely change its state in less than a year? Well, okay, so I should backtrack a little bit. So first of all, the kind of early studies kind of confirm that this is a disk accreting in there is a disk involved and it is accreting at some kind of high rate. Let's get that straight. But what's the problem with the 1 year thing? So think about how long does it take Earth to orbit the sun? A year. And how far is the Earth from the sun in astronomical units? Work. Yeah. And so the basic theoretical understanding is if you want a disk to go into outburst that fast, you have to disturb the innermost region because you have to disturb it inside of 1 AU because that's the dynamical time is the fastest thing that can happen. And so you have to disturb it in the innermost regions as fast as possible. Make sense? Yep, so this is really hard. And so really hard brings you a host of theoretical explanations. So that's just the kind of text quotes for this kind of thing. Explain the last time, you have to explain the fast rise time, you have to involve disk regions smaller than 1 AU because disk evolution will occur on longer than orbital period timescales. Yep. And so therefore you get, well, how do you do that? You have to make a disk go into something violent happening in the inner region. So thermal instability is kind of the main model for this. But maybe thermal instability has to be triggered by something. So maybe you disturb the disk and then it goes into thermal instability. So maybe you got planet-disk interaction triggering thermal instability, but you're trying to trigger something in the inner disk. Maybe you tidally disrupt young massive planets and then plunk them in the inner disk. Maybe you pile up material and it goes whoomp in the inner disk. Maybe you get, some outburst in a self-gravitating disk. Maybe you have a sudden increase in turbulence because you switch from one instability to the other. How can we help here? Theory models, how do you decide? Go observe the universe. All right, so actually, here's our theory model, which I'll tell you why it's wrong. But so we started to try to model this thing, so we thought we were being clever. But actually, I'm going to show you something dumb, which is we thought, well, let's try and do the radiation response of the disk. So let's take a disk. It's irradiated by the central star, but if you start accreting a bit of material, you're going to increase the luminosity of the star, and maybe this is kind of some feedback cycle. So that's what we wanted to do. We wanted to treat the heating cooling self consistently. So run this on the fly, Monte Carlo, ready to transfer. It sounds clever. Bang a star through it, see if that increased the accretion rate, increase the m dot, and therefore give us a rise in accretion luminosity, and maybe this would feed back. But actually, this is what happened. So we bang a star through a disk, and we're following the thermal response of the disk. So I'm plotting the density at the moment, but I'll show you the temperature in a minute. So we're computing the radiative transfer like every few time steps. And this is the accretion rates. So the thing we were trying to make work was the bottom line, that's the primary. So there's a 2 orders of magnitude jump here, which is about right. So we're going to make m dot go up by 100 times. but we made it last about, well, not even a year. And then it went back to 0 on the, so we were basically, because we didn't disturb the inner regions, we didn't do anything to the primary. But what did we do? Well, the secondary got a huge grab of material and it went into outburst very fast. Right? So we puzzled over this. We thought we'd done the wrong thing. We made it do the wrong thing because that thing's got into outburst, but the primary hasn't changed at all. Then we went and looked a bit more carefully at the observation. So this is FUORI. This is what it looks like in scattered light. The primary star, which is the one in outburst, is here. First of all, what's this thing? I think it is. It's another star, all right? And in ALMA, you can actually see there's 2 little compact disks. So there's 2 stars that are very close to each other. That's a clue. Okay, so what do you think the companion mass of FUORI is? So it's the one in crazy outburst is here. It's 200 solar luminosities. Its mass is like an M dwarf. What do you think the mass of the little disturbing thing is? In fact, so it's accreting at this very high rate. FUORI South is doing absolutely nothing. It's 2 solar luminosities. It's 1.2 solar masses. So it's the primary. It's doing nothing. Yeah, and it's accreting at a very boring rate. So nothing's happening on the primary. A lot is happening on the secondary. And so our explanation for this was, well, if you bang them into each other and one star penetrates the disk of the other, that would happen naturally. Okay, so it also explains some weirdness. So FUORI itself looks like an M dwarf with a wrong temperature. So it explains some of the spectral weirdness, which is good. Okay, so what's wrong with all these models? They're explaining the wrong stuff. Yeah, so we're explaining the wrong object in outburst here because the outburst, you're not trying to make a disk go bang in the middle. You're trying to make a disk go bang on the other object, at least in FUORI. So we can't generalize to the class, but we can say in this case, something else is going on. And so in a flyby scenario, you do get that for free. And so here's the temperature map. So if we look at the temperature, again, we're doing this on the fly Monte Carlo. So we can get the change in the disk temperature. And you really make, of course, because you're eating at a crazy rate, and we're taking the accretion luminosity into account in the radiation, you really heat the disk like crazy. And when I mean like crazy, I mean you heat it past 1500 Kelvin. Yeah, which is then, you start to melt stuff. And indeed, if you look at observations of outbursting young stars, you find melted dust, crystalline silicates, lots of like funky heating going on. All right, so you explain a bunch of things. So I don't think everything's right here. But one of the things is you just get these inflow motions and outflows. You get a high mass companion not in outburst. You get temperatures above 1500 Kelvin because of the accretion burst. So you start to make things like this in a disk. Okay? Maybe. You get a moving snow line. And remember how we got to this model in the first place? How did we get to this model in the first place? We're trying to think about how you grow stars. So it's, if you want to grow a star like the sun, then all stars have to go through these bursty phases. And so maybe it's just the common path is you go through these kind of outbursts. All right? But the thing I took away from this, which is more general, is if you then look at how the secondary actually accretes the material when it's in this high state. Remember the discussion we had about disks and how much they can accrete. How is the secondary accreting when it's in the high state? The movie plays. I think it's just playing slowly. But there you go. You got the preview of the conclusions. I want to just take you back here. So the high state is basically this. So if you want to transport angular momentum faster than a disk can do it, what's the best way to do it? Smash a stream into another stream, and you drop a lot of low angular momentum material onto the central object. So the common theme here is that what the flyby did is just spray a lot of material out of the plane, and that material then rains back down. And in fact, when you back to something that looks like a vaguely normal disk is when this accretion rate's dropping like crazy back to normal viscous accretion. So my argument is that what's happening in the high accretion mode is very non-disk-like accretion. And of course, that's been a huge discussion in the field, is basically you find evidence of these kind of streamers and stuff, which is just part of the star formation process, is you are dumping material from a turbulent cloud. And this is probably, while a flyby or a binary interaction is one thing that can trigger that kind of flow, you also get some flows like that quite naturally in a turbulent cloud. So probably the common theme is just this direct dumping of material and direct cancellation of angular momentum is a lot easier than trying to like do this kind of viscous spreading in a disk. Make sense? All right, so also, this is how we think disks are made in the first place. So if you take a simulation of star cluster formation and you say, let's look at how you make all the protostellar disks, of course, the whole game in the first mega year is this kind of violence where you're making a cluster of stars, they're interacting, you're reforming the disk multiple times, and you're decaying from this like random collection of stars into some kind of stable arrangement of stars. So single stars like the sun get ejected, the disk has been truncated by some kind of tidal interactions, goes on to live its life. Okay, so this is our picture of star formation. And why is the disk of the solar system misaligned to the spin plane? Because you might form your disk 3 times, and the last one you got left with is the one that formed planets, for example. All right, no one's getting too angry just yet. All right, but you see lots of evidence for this in the disk population. So one of the things that people are going after with ALMA now is just the population of compact disks. So we observed kind of, we tried to study all the fancy ones up the top, but there's a lot of disks that are just really small and compact. And compact small disks is what you get by tidal truncation in a kind of clustered environment. The other thing we're learning from observations is that disks, in fact, 1/3 of them show evidence of ongoing environmental interaction. So where you really are dumping material in this kind of streamer-fed modes from the cloud. So this is normal operation of disks in the real universe. All right. In fact, we also have direct evidence for this kind of dynamical interaction. Does anyone work on galaxies here? Someone stick up for the galaxies. Is anything sounding familiar? If I said I'm going to model a galaxy as an isolated object, you would tell me I'm an idiot because we've been observing this kind of thing for a long time. Yeah, which is just gravity doing its thing. And so it's probably not a surprise that we're starting to find the same kind of thing in the protostellar disk population. It's still gas, gravity, some kind of interaction. And so that's just gravity doing its thing. All right, so, well, in fact, I'm going to skip a little bit, but there's an even more direct argument which is if you plot the size distribution of protostellar disks, then actually what you get out of well, first of all, there can be quite different star-forming regions that have the same disk size distribution. So why is that? Wouldn't you expect a different size distribution in a dense cluster compared to a not dense cluster? And also that kind of matches what you get out of a simulation that just does a bunch of stars interacting in the cluster. So why does that work? How can a region like Orion have the same disk size distribution as a region like Lupus or Taurus, which is a more local star-forming cloud? Also, I want to take you back to the kind of mass that stars are born with. So basically, clouds fragment until the opacity limit, and the opacity limit for fragmentation is about 5 Jupiter masses. So you basically form a lot of low mass seeds that then interact to make larger objects. Slight going maybe. But basically all stars are multiple of Earth, and then the system decays. So even if you have a small patch of a molecular cloud, you're going to make a decaying n-body system. And it's the decay of the n-body system that sort of sets this size distribution. And so you don't have to have like a giant cluster interaction. You have a small n cluster, and you can still get the same size distribution out. All right, let's move on a little bit. So there are other things that can set the disk size. This is oversimplified. But tidal truncation is, I think, part of the story of what we're seeing in the disk population in clouds. All right, let's come to the solar system. Okay, so if you plot the material in the solar system, and all I'm doing is downloading the minor body distribution and plotting inclination as a function of pericenter separation, then you notice something really obvious, which is that after 47 EU, there is absolutely nothing in the plane of the solar system. There are no minor bodies outside 47 EU in pericenter. So if you plot apocenter, or sorry, if you plot semi-major axis, then things have moved. But pericenter preserves kind of something about, well, if you start scattering these objects, then you don't change the pericenter. So you scatter in energy but not angular. Okay, so why is the solar system, why does it just end? And everything outside of 47 EU is inclined and eccentric. So these are the trans-Neptunian objects like Quaoar and Sedna and all these objects. Why are they sprayed like that? Indeed. So this is called the Kuiper Cliff. It was a problem in 1997. The problem hasn't got any better, so it's not some sort of selection effect. What do you think the explanation is? We're just 25 years late. But yeah, so there was like Kenyon and Bromley, 2004 Nature paper. If you have a stellar flyby truncating the solar system, then you spray this material on inclined and eccentric orbits. So people just kind of go, yeah, but it's kind of special. But I guess part of the argument here is that this is what happens to all disks. And therefore, it's just the closest encounter the solar system had, but probably all solar systems have an encounter at some distance. And therefore, this is just telling you the closest one that the solar system had. And if you put this together with some of the other evidence, like we got melted dust, how do we melt dust? Outburst events. How do we spray material into eccentric orbits? How do we grow the star in the middle? Outburst events. Yep, how can we trigger an outburst event? We have flybys. Yeah, so some things start to work here, and the whole picture is not put together, but you start to think, actually, if you think about the environment in which the solar system forms, some of these old puzzles start to make sense as the common mode of star formation, but not some like weird thing that only happened in a special case. All right, there's another little subtopic here, which is about disk heating, and it also relates to the environmental interaction that we're seeing in disks. Is that in these kind of flyby simulations, you can figure out how much the disk is heated, and in particular, you can take account of how much heating would come from the shocks that you make in disks. All right, so most of the heating comes from the central object and the accretion luminosity, but you can add the heating from the shocks, and we did that, and that's the bottom picture. And if you don't take that into account, then that's the top picture. Okay, you see any difference? There's like 10 or 20 Kelvin in there, maybe 50, but not much. So why is this important? This is also seen observationally. So if you make a model of the spectral energy distribution of F-Uori and you ask where does the energy come from that illuminates the disk, then it's basically all the contribution to the SED is from radii inside 3 stellar radii. 1 stellar radius, 3 solar radii. This is like crazy inner edge of the disk. So it's not anything like the stuff in the outer disk. So it's the inner things irradiating the outer things. Why am I telling you this? Because we know this, and we know this from star formation too, that the irradiation from the star dominates everything else. Okay? But it's important for one of the other mechanisms we talked about, because the standard way that we study gravitational instability is we take a disk, we assume there is no heating from any central object, and we watch it go with some cooling, which is then balanced by heating from shocks in the disk to get this kind of self-regulated turbulent state in the disk. Following? Yes, no? All right, so the standard picture is you add some kind of prescribed cooling as a function of that's proportional to the omega in the disk. You watch it go, but of course the shocks hit the disk, this term cools the disk, and so a disk which would be unstable can self-regulate because the tomb ray Q initially was unstable, the disk heats back up because of the shocks, and therefore you self-regulate and Q goes back up again, but then you cool again, and so you go back to this Q equals 1 state. So a disk behaves like a thermostat in this picture. But now what's wrong with this picture for protostellar disks? Shock heating actually does nothing. So in a protostellar disk, we should have the heating from the central object. And so people have tried to study this. But again, we have a tool that we can try and attack this problem. So we can do this kind of on-the-fly Monte Carlo. So we can simulate what happens. We put a gravitationally unstable disk. We take the heating from the central object. The heating is dominated by the central object, so there is some heating from the shocks. But of course, basically the central object bakes you in a more or less constant radiation field. And so the disk goes gravitationally unstable, there's some viscous spreading, sigma drops, and so Q just kind of slowly drops with time, slowly increases with time, sorry, because sigma drops. And therefore the disk just stabilizes. Why is this relevant? It's because if you want to claim that spiral structure in protostellar disks is caused by gravitational instability, you better not claim it by trying to do shock heating, balancing, cooling in the outer disk, because that's not what happens. Okay, but what could happen instead? How could we get this material to go back to being unstable? Sorry, I'm asking too many questions. Exactly, so we could add, you've seen this before. So we could add mass, right? So if we are observing gravitational instability in the disk population, then maybe what's happening is instead of taking away heat, maybe what we're doing is adding mass. So we're baked in this radiation field from the central star. And so this is important because a disk like AB Auriga looks for all the world like it's gravitationally unstable. And got these large-scale spiral arms, beautiful scattered light emission. But it's kind of puzzling because m dot's not particularly high, and the disk mass is not particularly high either, although there's a big uncertainty on disk mass. So what does it mean? Is this thing gravitationally unstable or not? We're not accounting for the radiation from the central star here if we're claiming that it is. It's the missing ingredient. Well, you can see there's a connection to the environment. Okay, so this is, if we want to make things that accrete at a high rate, we need to bring things in from the surrounds. All right, so I'm trying to speed up. But basically, you can self-regulate a disk if you add mass. So you can make these large-scale spiral arms, but you need to bring infall, or here we're just injecting it in a ring, but you can pump material on some kind of stream and tip the disk back into gravitational instability. It's a very different picture to a heating and cooling. So it's more like a bathtub rather than a thermostat. So you're continually adding material, but it's also going down the drain. But you can make things work if you don't consider a disk as being in isolation. All right, so there's some little differences, but you could explain things. But there's one caveat to this, which is that maybe you don't need the gravity at all. So actually, if you just add material to a disk, and Kay's is here has done some of this kind of work, if you simply add material to a disk, actually you also drive a lot of angular momentum transport because you're dumping material with the wrong angular momentum. And so infall actually produces spiral arms without anything to do with the self-gravity acting. And so we need to disentangle these two things. And in fact, so Josh did a really good job of this. So this is exactly like the cloud capture model, basically, for how you make accretion disks, which is dumping material from the environment. So that's similar picture. You need to, if you want to make things go bang, you have to basically directly cancel angular momentum. So actually you can do the job. So this is one we just submitted, is that you can actually reproduce nearly all of what's going on in AB Auriga just by dropping some material on the disk. No gravitational instability involved. And so again, maybe the picture that's more important is the connection to the environment, and this kind of dumping and cancellation of angular momentum is actually driving a lot of angular momentum transport here without needing any kind of instability. All right, so I'm going to try and finish there. I'm going to skip a couple of things, but there's another way you can misalign and warp disks, and that's put a misaligned binary in the middle. This is also observed in the real disk population, so it's not fictional anymore. Also drives this like strongly modulated accretion rate, which is driven by this kind of processing rings from a binary. But misalignment is the common story. There's also the same story that we've been studying in black holes. I said I'd mention black holes, so a little token mention for the black hole people in the room. But if you want to feed a black hole from a star, then the way that you transport angular momentum and form a disk is that the star is in orbit, goes into orbit around the black hole, but the black hole induces precession just to the GR that's going on. And what does precession do? Well, it makes the stream self-intersect, and then you basically directly cancel angular momentum and you start feeding the black hole. So it's the same story. If you want to make things accrete fast, you need some kind of thing which is not some sort of ring spreading in a disk. You want to make things directly cancel angular momentum. So that's sort of my takeaway here. So in some of this discussion about what's the viscosity, we're missing a bigger picture. This is kind of the small scale drip feed, which is not to say that these mechanisms don't operate, but we should not forget the bigger picture, which is just that the best way to transport angular momentum is just to cancel it. And that's my broad conclusion. So if you want to get rid of angular momentum in a disk, you just basically go like that. All right? And so that's more or less the summary from everything we learned so far, is you can forget about disks in a lot of cases, actually. If you want to do a lot of angular momentum transport, you just do it in a dramatic way. And nature seems to be doing that in a bunch of cases.
Great. Thank you for this very interactive talk. Questions, particularly from students and early career researchers to start. Since we've had lots of awkward pauses already, we can have one more.
My question is, do we have a rough time scale for how often stars will interact in these young clusters? Like, how often should we see these kind of flyby events?
Well, so yes, I mean, a lot of it happens in the embedded phase, of course. So in the early stages of star formation, what we call the class 0 and 1, it's all by definition embedded in the cloud. So a lot of it's going on during that first mega year. And then there's basically an exponential drop-off of the probability of that happening to you as a function of time. So first 100,000 years, everybody has an interaction, but then it drops sort of exponentially in a way that looks very much like the disk fraction as a function of time. So you've got, okay, so what's interesting about the time scale? So in the solar system, for example, this chondrule formation is thought to be like several mega years after the initial kind of what they call the CAI moment. So what you need is to have some outburst that happens later. And so the sort of flyby scenario is, well, I'm proposing it as something that can happen later, which can re-trigger a kind of outburst that would give you like disk heating and this kind of melting that you need. Speculation.
Do you attribute any big significance to the 7-degree tilt of the sun with respect to the ecliptic, or would that be just like a natural?
No, my take on it is that it would be, I mean, it would be special if it was 0, but 7 degree is just a random number that could be anything between 0 and 180.
Is that something we have observations for other stars about?
Well, so we have quite a bit of evidence in the exoplanet population that, so what's called the Russell-McLaughlin effect, which is that you can track the stellar spin from the transits, and most of the time they're not aligned. So there's very much evidence that the exoplanet populations are misaligned like that in some fairly random way.
More questions?
Daniel, very nice. Thanks for this beautiful overview. What dynamics in context can do to us. I think most star-forming calculations, in particular the one from the colleague in Exeter that you have shown, starts with a very, very, very specific initial condition that you will probably not find realized in nature. without a history. And if you build it from a proper turbulent flow, things are much less violent. There will be much less flybys and so on and so forth. So I think it's probably more likely to think of the overall turbulence you have in such a star-forming cloud anyway to give you accretion events from different angles with different angular momenta brought in and so on and so forth, than to talk about flybys of discrete objects. But the question I have is a very different one. You always talked about the spin of the star with respect to the disk plane. But if you look at Venus, for instance, right, it is completely tilted. So there is also collisions within the planets. And I'm wondering whether that stuff also plays a role in the picture you have painted.
Certainly. So I mean, giant impacts is the way you explain all misalignments in the solar system, according to standard wisdom. So, I mean, there's various problems with tilting. I'm not an expert by any means on that kind of thing, but there's lots of problems with, you need quite special impacts in special cases. So I don't know, but there are other things that can work. So one thing we've been thinking about a little bit is, for example, circumplanetary disks are sort of tilt unstable. So they do, if you get them a little bit of tilt, they tend to go wobbly. So if you had a circumplanetary disk around Uranus, for example, you might be able to take the planet with you. But that's just, I don't know is the short answer. But can I just go back to this one about do you have flybys in low density environments? So I have a plot for this, which is, so you can forget about Orion, you can forget about Ophiuchus, they're too clustered. Let's talk about the least clustered star-forming region, and let's forget about the main thing that's too clustered. Let's look at the thing which is like completely isolated and nowhere near anything else and shouldn't be influenced by forming in a cluster. So the least dense thing you can think of in the local universe. And there's two objects I'm going to select here. Well, they're just, the very isolated things in Taurus. And a couple of people in the group on Friday know what these objects are, so you've done your homework. What's the objects? One of them is RW Riga, and the other one is so here's a recent paper on RW Riga. It's called Multiple Stellar Flybys Sculpting the Circumstellar Architecture. So there is direct evidence for like some kind of violent binary interaction between the disks going on in that case. The other object is the prototypical young star, which is Titori. So what's Titori? It's a crazy triple where the star from one is penetrating the disk of the other. It has these weird dimming events every like 20 years or something as the secondary goes through the disk of the other one. So this is observationally reconstructed. So I hear on the like Matthew simulations are too dense kind of argument, but clearly observation we see even in very isolated regions that multiplicity is the story and there's observationally tidal interaction going on. So I agree that you can't infer that from a big cluster simulation, but we see direct evidence of disk truncation even in what they call these small n groups.
More questions?
So if I understood correctly, the secondary is helped in the accretion by flyby from a more massive primary.
Yep.
So then what happened to the primary? Did they have another more massive? So it's like how does the picture goes between different objects?
So the reason why the outburst happened on the secondary in that case is because we didn't put a disk around the perturbing object. So what we did in a follow-up study is we put disks around both objects and then collide things into each other. And it's obvious afterwards, but not obvious before. But you accrete most of your material from the other disk. And that's simply because when you bang things into each other like that, the low angular momentum material is what you accrete. And so the low angular momentum material comes from the thing that banged into you, basically, and that's what rains down. So that's interesting because in the solar system context, again, this late infall is a kind of tiny difference in isotope ratios. So you need a kind of fresh dump of material, and that could come with this kind of late infall flyby event that also did the truncation. So the important thing is, getting the source of low angular momentum material. So for example, you can make both stars go into outburst in that case, but it's dumping material with low angular momentum that makes that happen.
I don't see any more hands raised. So before we thank Daniel again, I'll remind that there's meeting with the students after the talk, and there's also dinner at Dorfschenke later. If you're interested, just talk to Mike. So thank you for this excellent talk.